Let's talk about the distance problem. Earlier, we saw that if you know the distance, and we frame this as position, at any given time, then you could find the velocity at a given instant. So just as a quick reminder, the velocity function v of t is equal to s prime of t. So we took the derivative of the position function in order to get the velocity. Now we want to do the opposite. If we know the velocity at any given time, we want to find the distance traveled. Let's consider the constant case first. In other words, let's assume that the velocity is constant. Then we're going to be able to say the following. Now, you guys are probably familiar with this distance is equal to the rate times the time, right? Well, this rate is really our velocity, v of t. So if we had a constant velocity type situation, then the distance would just be equal to the velocity times time. But remember, we're saying in this case that this number is a constant. So if I were to draw a picture, my picture would look something like this. Okay, here's our axis. We'll have a time over here. We'll have velocity over here. We could label a point A here and a point B here. I could have my velocity be a constant function. That just means it's a horizontal line. And if you calculated the velocity, which is a constant in this case, times the time, this would be nothing more than the area of a rectangle, right? So I could draw a rectangle, and then I could color my rectangle in. And after coloring my rectangle in, the area of this rectangle would be my distance. So, so this area, the area is equal to the distance. I hope you could see where we're going with this. Now we want to consider the case where the velocity is changing. So it's not going to be a constant. It's not going to be a constant horizontal line. Instead, it's going to be changing, like something like this. Here's an example. All right. So I want to label my axes over here. I'm going to label the bottom axis time. And let's pretend that this is measured in seconds. And then I'll label my y-axis. Let's label that velocity. And let's pretend that in this case, it's going to be meters per second. And then what we can see is that if you were to multiply the units of the velocity times the time, in other words, if you had velocity times time, the units would be meters per second times seconds. The seconds would cancel out, and you would end up with the units of meters. All right, and this is distance. Now, when we look at this function over here, this is a continuous function as I've drawn it. What we're going to do is we're going to approximate the area under the curve basically using rectangles. So let's say I used left endpoints. Then my first rectangle would be there. My second rectangle would be there. My third rectangle would be here. My fourth rectangle, remember I'm using left endpoints. My fifth rectangle is up here. My sixth rectangle is up here. My seventh rectangle is here. and my 8th rectangle is here. So remember, this is just an approximation. I can even write in the areas over here. So this has an area of 1, this is an area of 2, this is an area of 3, 4, 5. This drops back to 4, 3, and 2, right? So I could take my calculator, I could add up the areas of all of those rectangles, and I would get a nice area. So let me move this page up a little bit. We're going to say the following. We're going to say the distance is approximately equal to the sum as I, in this case, goes from 1 to 8. And we're going to have the velocity at some, we're going to call it t sub I star. In our case, we're using the left endpoint times the thickness of each rectangle. So that's going to be delta t, right? So I can describe what this is. Let me write a few more things over here. This ti star, in our case, in this case, we're using the left endpoint. And we also know that our delta t is going to be the length of the interval, which is b minus a, all divided by n. Okay, so in our case, it's going to be 8 minus 0 divided by, we have 8 rectangles, so that's 8. So that's just equal to 1. All right, cool. So why don't we, I guess, actually calculate it in this particular instance? This approximation is going to be equal to 1 times 1 plus the height of the rectangle, which is 2, times the width, which is 1, plus the height of the rectangle, which is 3, times the width, which is 1, plus 4 times 1, plus 5 times 1, plus 4 times 1, plus 3 times 1, plus 2 times 1. So popping all of this into our calculator, we get 24 meters. And that would be our approximation in this case. Now, I want to highlight this fact that the distance is approximately equal to the sum as I goes from 1 to 8, v of ti star times delta t. Now, I want to modify this a little bit. In general, we don't have to sum to 8. We can, if we want to make it the most general thing, we would just sum to n. So let me replace that 8 with an n and then re-highlight here. So this highlighted formula is our approximation for our solution to the distance problem. All right, folks, we will work on this some more in class together. Take care.